Pick a single strand of your hair and look at it. Now imagine a thread 5 times thinner than that. So fine you can barely see it on your fingertip. That thread is stronger than steel. Not a little stronger. By weight, more than 10 times stronger. Bundle a few thousand of them together, weave them into a sheet, and you get the skin that wraps the wings of an F-22 and an F-35. The fastest, deadliest fighter jets ever built fly on a material that starts as something soft and white, like plastic yarn. And here's the part nobody tells you. To turn that soft white thread into something that can hold a 40,000-pound jet together at twice the speed of sound, you have to nearly burn it alive. Stay to the end, because the moment the color changes from white to black is the moment a fiber becomes one of the most valuable engineered materials on Earth, and almost nobody has ever watched it happen. Let's start with what this stuff actually is, because the numbers don't feel real until you hold them up against something you know. A single carbon fiber filament is about 5 to 10 microns across. A micron is 1/1000th of a millimeter. Your hair runs around 70. So we're talking a thread you literally cannot split with your eye. Now take that thread and pull on it. Aerospace-grade carbon fiber holds a tensile strength of roughly 3 gigapascals. In plain terms, by weight it beats mild steel more than 10 times over. Steel sinks, this floats and shrugs off the load. That combination, almost no weight plus brutal strength, is the holy grail for anyone building something that has to fly. Every pound you cut off an aircraft is a pound of fuel you save, or a pound of missile you can carry. And it all begins with a spool of soft white fiber called PAN, polyacrylonitrile. About 90% of all the carbon fiber on the planet is born from that one white thread. It looks like nothing. It looks like fishing line, but it's the seed of the whole thing. So how do you turn fishing line into something that builds a fighter jet? You torture it with heat, in stages, and the first stage is the one that changes everything. The white PAN fiber gets pulled, slow and steady, through a series of ovens filled with ordinary air, heated to between 200 and 300 degrees Celsius. That doesn't sound like much next to what's coming, but watch what it does. As the fiber crawls through that heat, held under tension so it can't shrink and curl, its molecules lock together into tight, ladder-like rings. And the color shifts, white to yellow, to a deep brown to black. You can see it happen down the length of the oven, like a slow fuse burning in slow motion. This step is called oxidation or stabilization, and it is the make or break moment. Get the temperature wrong by a little, rush the speed, and the whole batch is ruined. Here's the catch that makes this material so rare. Every factory guards its exact recipe. The precise temperatures, the precise tension, the precise speed through the oven are some of the most closely held secrets in the industry. 2 companies can buy the same white pan, and one comes out with aerospace gold, and the other comes out with garbage. That single difference is worth billions. Now comes the fire that actually creates the carbon. The black, stabilized fiber leaves the air ovens and enters a sealed furnace with no oxygen at all, just inert gas, because at these temperatures, even a whiff of air would make the fiber simply burn away to ash. Inside, the heat climbs past 1,000 degrees Celsius, and for the highest grades, it pushes toward 2 and even 3,000. Think about that, 3,000 degrees, hotter than molten lava, hotter than most metals can survive. And the fiber doesn't melt, it transforms. Everything in that thread that isn't carbon, the hydrogen, the nitrogen, the oxygen, gets blasted out as gas and driven off. About half the original mass vanishes into thin air. What's left behind is over 90% pure carbon, with the atoms locked into long, tight sheets running the length of the fiber. That alignment is the secret to the strength. The atoms are gripping each other in nearly perfect rows, end to end, so when you pull, you're pulling against the raw bonds of carbon itself. This is no longer plastic. It's no longer yarn. It is a thread of nearly pure crystal carbon, thinner than a hair, that you could hang a small car from. But a single thread, no matter how strong, is useless on its own. You can snap one filament with your fingers. The magic is in the numbers. Those filaments get bundled into what's called a tow, and a single tow can hold 3,000, 12,000, even 24,000 individual fibers running side by side. From there, they get woven, on looms that look almost like an old textile mill, into flat black cloth. Run your hand over it and it feels like dark silk. but it shimmers and it's bone dry and it weighs almost nothing. That cloth still isn't a wing though. To build the skin of a jet, the fabric gets soaked in epoxy resin, layer on layer, the threads turned in different directions so it's strong in every direction at once. Then the whole stack goes into a mold, gets sealed in a vacuum bag, and rolls into an autoclave, a giant pressurized oven the size of a tunnel. Under heat and crushing pressure, the resin flows, the air bubbles get squeezed out, and the layers fuse into one solid piece. Because a single hidden air pocket, one bubble you can't see, becomes a weak spot that could split open under the stress of flight. When it comes out, it's lighter than aluminum, stiffer than steel, and shaped like the exact curve of a fighter's wing. So where does all of this end up, and why should you care? Look at almost anything that flies fast or far today. The F-22 Raptor, the F-35, their wings and skins are packed with this material, around a third of the entire jet by weight. The Boeing 787 that carries people across oceans is half carbon fiber composite, wings and body. And here's the twist on the price. The raw fiber, by the gram, is actually cheap, just a few cents. But by the time you've turned white PAN into pure carbon, woven it, layered it, and cured a flawless, certified, defect-free part stiff enough to survive a dogfight, you're looking at a finished material worth thousands of dollars for every kilogram in the air. And the program that flies on it, the F-35, runs well over $1 trillion across its life. That's the real story of carbon fiber. A thread thinner than your hair, born soft and white, nearly burned to death in 3,000 degrees, reborn as black crystal, and woven into the wings that rule the sky. Next time you see a fighter jet carve across the clouds, remember what's holding it together up there. And if you want to see how the engines that push those jets past the speed of sound are forged, that one's even harder to believe. Keep watching.
What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal, at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, tungsten's used to make ballasts and counterweights in race cars, aircraft, and yachts thanks to its crazy high density. It's even a component in some jewelry because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal, or tungsten oxide equivalent, fluctuates, but in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible. Without this resource, half of humanity would starve, and 99% of people have never even heard of it. I'm standing 2,300 feet underground in a mine that rarely lets cameras inside. Every single day, they set off explosives down here, and the rock is so brittle that one mistake, and the tunnel disappears along with everyone in it in mere seconds. This is potash. Only a handful of facilities worldwide control its extraction, and today, one of them opened its doors to us. To get 1 ton of final product, you need to process 4 tons of raw ore. And how exactly that happens, and what these giants hide behind their metal gates, you'll see by the end of this video. Where do you find it? Deep underground. Very deep. We're talking depths ranging from 1,300 feet to 3,000 feet, sometimes more. It's like descending to the bottom of the Grand Canyon, then going down that same distance again. But how did it end up in Earth's depths? To understand that, we need to take a journey through time, hundreds of millions of years back. In those distant times, where modern potassium salt deposits exist today, there were massive inland seas and ocean bays. These seas were shallow and existed in extremely hot climates, similar to deserts. In these enormous bodies of water, the water constantly evaporated under the scorching sun. When water evaporated, the minerals dissolved in it, like common salt and, well, potash, started settling on the bottom. Think of it like a cup of really salty water you left out in the sun. The water disappears, but the salt stays behind. But on the scale of entire seas, this process took millions of years. Layers of these minerals piled up one after another, forming massive deposits. Eventually, these ancient seas dried up completely, and other rocks accumulated over the salt deposits: clay, sand, limestone. Millions of years of Earth's tectonic activity, continental drift, mountain building, buried these salt layers even deeper below the surface. That's why we find them at depths of thousands of feet. The potash mine itself is a massive, sprawling system of tunnels, stretching for tens, even hundreds of miles. It's an underground city where hundreds of people and giant machines operate. The temperature here is constant, around 75 degrees Fahrenheit, but humidity can be pretty high. And this is where the real challenges and risks begin. These rocks containing potash are called sylvanite. They're brittle, very brittle. One wrong move, one miscalculation, and a collapse can happen. This isn't the kind of work where you can let your guard down. Every miner, every engineer knows the price of a mistake. These are high stakes, with human lives and multi-million-dollar investments on the line. How do they extract potassium? First, massive drilling rigs create blast holes, small openings in the rock. Then they load them with explosives. Yes, actual explosives. And here come more risks. Calculating the amount of explosive, where to place it, timing the detonation. All of this demands tremendous experience and precision. The blast hits, a deep rumble, and tons of rock come crashing down. After the explosion, another set of giants enters the picture: mining machines. These are massive pieces of equipment that look more like tanks with enormous cutting tools. Their job? Collect the blasted rock and load it onto conveyors. Each machine weighs dozens of tons and costs millions of dollars. They run non-stop, slicing through rock and breaking it into smaller chunks. It's incredibly dusty work, which is why ventilation in the mine is a matter of life and death. A constant flow of fresh air keeps workers safe and maintains visibility. And even with that, everything gets coated in a layer of dust. After traveling hundreds, even thousands of feet underground, the potash concentrate, a mixture of potash salt, common salt, and clay, reaches the surface. And this is where the second, equally complex and fascinating part begins: processing. This isn't some dirty mine anymore. It's a massive, roaring plant where chemical processes bubble and boil. Separating the potassium from all the other junk? That's one hell of a challenge. First step, crushing. Giant crushers turn large chunks of rock into tiny bits. You need this so the next processes can work the material more efficiently. Massive hammers that could demolish a car crush rock here just as easily. You could watch this for hours. Mountains of rock transforming into sand. Next up, the crushed material gets mixed with water. Yep, just water. This is called slurry. This slurry passes through special hydrocyclones, these massive cone-shaped machines that use centrifugal force to separate heavier particles from lighter ones. It's like a spin cycle in a washing machine, but for minerals. This gets rid of some of the clay and other light impurities. And here's where it gets really interesting: flotation. This is the heart of the potash enrichment process. Basically, we make potassium salt float while regular salt sinks. Sounds weird, right? But it works. Special reagents are added to large vats of slurry. These are chemicals that stick to the potassium salt, making it hydrophobic, meaning it repels water. Then air is pumped through this mixture, creating millions of tiny bubbles. The potassium salt, which now hates water, sticks to these bubbles and rises to the surface as foam. Regular salt stays at the bottom. This foam that's risen to the surface, that's our valuable potash concentrate. It gets collected, dewatered, and then dried. Drying happens in massive rotating kilns or dryers, where temperatures can hit several hundred degrees Fahrenheit. This removes all the moisture and gives us a pure, dry product. And right here, we've got our final product, potash, ready to be packaged and shipped to farmers around the world. But the process doesn't end there. Because it's not just about extracting potassium, it's about doing it as efficiently and safely as possible. The water used in the flotation process gets cleaned and cycled back into production. The waste left after separating out the potassium, that's just regular salt and clay. They get disposed of responsibly. At some facilities, that regular salt can even be reused. For example, spreading on roads in winter. From 1 ton of ore, we get only about 25% pure potash salt. That means to produce 1 ton of final product, you need to process 4 tons of ore. Picture this. To meet the needs of, say, an entire country in potassium fertilizers, millions of tons of rock must be processed every single year. We're talking massive volumes of work requiring enormous investments in equipment, technology, and safety. Why is this so expensive? And why are there only a handful of facilities in the world doing this? First, investment. Building a mine and plant like this can cost billions of dollars. This isn't something you build in your garage. Second, incredibly complex engineering. We're talking extraction at enormous depths, working with brittle rock formations, precise chemical processes. Third, safety. Every step in this operation involves risks, from mine collapses to handling chemicals at the plant. Companies spend millions training personnel on modern equipment and safety systems. And finally, it's a rare resource. Potash salt isn't found everywhere, and the places where it exists, these are genuine treasures. Did you appreciate this journey into the world of potassium? We've seen how this valuable resource is extracted from deep within the earth, how it's processed, and how it reaches our fields, helping us grow food. This is a story about engineering excellence, about massive machines, about people working in incredibly challenging conditions, and about a vital element without which the modern world would be completely different. And from you, a subscription. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, and we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material. Then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic, although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. Picture a single engine as tall as a 4-story building and longer than 2 city buses parked end to end. It weighs 2,300 tons. That's more than 350 full-grown elephants stacked into one machine. One piston inside it is taller than a man. The crankshaft alone weighs 300 tons. And when it runs, it puts out over 107,000 horsepower, turning a propeller bigger than a house. This is the largest engine human beings have ever built, and almost nobody has ever seen one in person. And here's the thing, nobody tells you. This monster turns over slower than the second hand on your watch, and that's exactly why it can move a ship the size of a city block. Watch to the end, because the part that holds the whole thing together is forged in a way only a few factories on Earth can pull off. Start with the scale, because the numbers don't feel real until you stand next to them. The biggest of these engines, the Wärtsilä Sulzer RT Flex 96C, stands almost 44 feet tall and nearly 90 feet long. Walking from one end to the other is about 30 paces, and it weighs 2,300 tons, the same as 11 fully loaded railroad locomotives. Compare that to your car. Yours makes maybe 200 horsepower. This thing makes over 107,000. More than 500 family cars bolted into one block of steel. And it doesn't scream like a race car. It thumps. Slow, heavy, deliberate. At full power, it turns just 102 times a minute. Your kitchen blender spins 100 times faster than the most powerful engine on the planet. That's the whole trick. Brute force, almost no speed. So, how do you build something this big? You don't pour it in one piece. Nobody can. The block, the cylinders, the crankshaft, the pistons, every part comes from a different forge, and some are the only ones in the world that can do the job. It starts in the foundry. The bed plate the whole engine sits on gets poured from molten iron at around 2,600 degrees. A single casting can weigh dozens of tons, and it takes a crane just to move the empty sand mold. When the iron pours, it glows white and runs like water. Then it sits for days, cooling slowly, because if you rush it, the metal cracks from the inside, and a crack you can't see at the factory will tear the engine apart at sea. One flaw, and a ship loses power in the middle of the ocean. Now we get to the part the engineers lose sleep over, the crankshaft. This is the spine of the engine, the steel bar every piston pushes against to turn the propeller. And on the biggest engines, it weighs around 300 tons, all by itself. 300 tons. Heavier than the Statue of Liberty. You can't cast a part like this, because cast metal is brittle, and this shaft takes a beating every second the engine runs. So it has to be forged. They heat a block of solid steel until it glows orange, then a press squeezes it with thousands of tons of force, hammering the grain of the metal into shape so it survives decades of pounding. It comes in sections, each machined to a tolerance finer than a sheet of paper. Only a handful of foundries on Earth can forge a shaft this large. This single part is why these engines can't just be built anywhere. Then there are the pistons, and this is where the size really hits you. The cylinder bore, the hole the piston slides in, measures 38 inches across, just over 3 feet. You could sit inside one. The piston that fills it is taller than most people, and it travels almost 8 feet up and down on every stroke. 8 feet. Most car engines move their pistons 3 or 4 inches. Each time it fires, the pressure inside is enormous, and the temperature climbs past the point where ordinary steel would soften and fail. So the piston crown gets cooled from the inside by oil pumped through channels drilled into the metal. 14 of these cylinders line up down the length of the engine. 14 explosions, firing in sequence, 100 times a minute, for years on end without ever shutting down. Here's a number that should stop you cold. The torque on the crankshaft, the raw twisting force, is over 7.5 million Newton meters. Torque is the muscle that turns the propeller. A strong pickup truck makes maybe 500 Newton meters. This engine makes 15,000 times more. That's the force it takes to spin a propeller the size of a small house through thick seawater while dragging 200,000 tons of steel and cargo behind it. And it does it sipping fuel. These slow-turning giants are the most efficient combustion engines ever made. More than half the energy in the fuel actually goes into moving the ship, while your car wastes most of its fuel as heat. That's why it runs the world's oceans. Now comes assembly, in a hall the size of an aircraft hangar. The bed plate goes down first, leveled to a fraction of a millimeter, because if the foundation is off, every part above it wears out fast. Then the crankshaft is lowered in by overhead crane, 300 tons swinging in the air, guided into its bearings by workers reading hand signals. The cylinder block stacks on top. Then the liners, the pistons, the connecting rods, each craned into place and torqued to spec. A single connecting rod weighs more than a small car. Bolts the size of your forearm get tightened with hydraulic tools, because no human arm could turn them. The build takes months. And when it's done, that engine has well over 250,000 parts inside it, everyone placed by hand. Before it ever touches a ship, the engine has to prove itself. They bolt it to a test bed, hook it to a giant brake that absorbs all that power, and run it. Cold start, slow warm-up, then harder and harder, until it's making full power on the floor. Sensors cover every surface, watching temperature, pressure, vibration, the bend in the crankshaft as it loads up. They run it for hours, at overload, hunting the one tiny problem that won't show on land but would become a disaster 1,000 miles out at sea. Because once this engine is sealed inside a hull and the ship sails, there's no pulling it out. It has to run day and night for the entire life of the vessel. 20, 30 years. Only after it passes every test does it get torn back down, packed into sections, and shipped to the yard. So, where does all of this go? And why does it matter to you? Onto a container ship, the kind that carries 20,000 steel boxes stacked 9 high above the deck. That engine, dropped into the belly of the hull, is the only thing moving every phone, every car part, every pair of shoes across the ocean to your door. Around 90% of everything traded between countries moves by sea, and almost all of it rides on top of an engine like this. The sneakers on your feet, the coffee in your cup, the screen you're watching this on. Everyone crossed an ocean inside one of these slow, thumping giants, burning heavy fuel oil, turning that propeller 100 times a minute, mile after mile, almost never failing. Because failing in the middle of an ocean is not an option. And here's the part that ties it all together. This engine almost never shuts off. From the day it's commissioned, it can run for months at a stretch, only stopping in port. It burns the cheapest, thickest fuel on Earth, a sludge so heavy it has to be heated just to flow through a pipe. And out of that black tar, it pulls more useful work than any engine ever built by hand. 2,300 tons of iron and steel, 14 cylinders, 300 tons of forged crankshaft, all turning slower than your second hand, moving the entire world economy across the water without anyone ever seeing it work. That's the real story of the largest engine on the planet. It hides in the dark at the bottom of a ship, and it never gets the credit. If this changed how you think about the stuff that shows up at your door, hit subscribe, and I'll show you the next machine most people never get to see. Your house has no electricity. Your phone doesn't exist. The internet is physically impossible. Electric motors of any kind can't be built, and human civilization is frozen in the 1800s with steam engines and gas lamps. All because we never figured out how to refine one reddish metal that conducts electricity better than anything else except silver, which costs 50 times more. Without this metal, every wire would need to be 3 times thicker and cost 4 times as much. Power grids couldn't reach beyond cities. Your electric bill would be $1,200 monthly. Today, we're going inside the factory in Utah, where this metal gets refined to 99.99% purity, and I'll show you why that purity matters, and what would happen if we used something else instead. The Kennecott Copper Refinery in Magna, Utah, sits 12 miles west of Salt Lake City, and has processed copper continuously since 1903. This facility receives ore from Bingham Canyon Mine 20 miles south, the largest man-made excavation on Earth visible from space. The refinery processes 300,000 tons of copper per year, and every step creates properties that make electrical civilization possible. Raw copper ore contains only 0.6% actual copper mixed with rock and minerals. If copper was never discovered, we'd use aluminum for electrical wiring. Aluminum conducts only 60% as well as copper, meaning you need 50% more cross-sectional area for the same current. Every wire in your house would be thicker and heavier. Building construction costs would increase 30% just from wiring. The first stage crushes ore into powder and mixes it with water and chemicals in flotation tanks. Air bubbles blow through, and copper minerals stick to bubbles and float as froth while waste rock sinks. The froth contains 30% copper, a 50-fold increase from raw ore. This concentration matters because copper's conductivity depends entirely on purity. Even tiny impurities dramatically increase resistance. 1% phosphorus increases resistance by 50%. 0.1% arsenic doubles it. Without purification, we'd use metals that lose huge amounts of energy as heat. Power companies would generate 3 times more electricity just to compensate for transmission losses, 3 times more power plants, fuel, and pollution. Concentrated ore moves to the smelter and heats to 2,200 degrees Fahrenheit. Copper melts and separates from sulfur and iron, which becomes slag. What emerges is blister copper at 98% purity. Better, but not good enough for electrical use. Copper's heat tolerance becomes important here. It carries high currents without melting, doesn't melt until 1984 degrees Fahrenheit. Aluminum melts at only 1221 degrees. In electric vehicle motors or transformers, aluminum would literally melt under load. Electric motors would need to be 3 times larger to keep current densities low enough. A 200-pound copper motor would weigh 600 pounds in aluminum and deliver less power. Blister copper moves to electrolytic refining, the most critical stage. Impure copper sheets become anodes in giant tanks with acidic copper sulfate solution. Pure copper cathodes sit opposite, and when current passes through, pure copper ions migrate to cathodes while impurities fall to the bottom. After 12 days, cathodes are coated with 99.99% pure copper. This extreme purity creates extreme conductivity. At 99.99%, copper conducts so efficiently that a mile-long wire loses only 2% power as heat. At 98% pure, that wire loses 15%. With aluminum at any purity, you lose 5 to 8%. The United States has over 600,000 miles of high-voltage transmission lines. If those were aluminum instead of copper, we'd lose 200 billion kilowatt-hours per year in transmission, enough to power 20 million homes. Your electric bill would triple. Pure copper cathodes get melted and cast into forms. Some become wire rod drawn through progressively smaller dies, creating wire from thick power cables to hair-thin magnet wire. Others get rolled into sheets for circuit boards and building materials. Each application requires different properties, but all depend on 99.99% purity. Copper's combination of conductivity and ductility becomes critical here. Copper can be drawn into micron-thick wire without breaking. Aluminum is brittle. When you bend aluminum wire repeatedly, it cracks. This is why every electric motor uses copper windings. The wire bends around tight curves hundreds of times during manufacturing without breaking. Without copper, we couldn't mass-produce electric motors. No motors means no electric vehicles, power tools, washing machines, fans, or pumps. Every copper batch goes through rigorous testing, and there's a specific reason purity standards are so strict. During the 1960s and early 70s, copper prices spiked, and builders used aluminum wiring in homes to save money. Aluminum was cheaper, but had higher resistance, running hotter under load. The real problem was connections. Aluminum expands and contracts more than copper when heating and cooling. Over months of electrical cycling, aluminum wire worked loose from connection points. Loose connections create more resistance and heat. The insulation would char and ignite. Between 1965 and 1973, tens of thousands of house fires traced back to aluminum wiring. Dozens died. Insurance companies refused to cover homes with aluminum wiring. That crisis proved copper can't be substituted. Today, every copper product goes through conductivity testing. Pure copper at 20 degrees Celsius has conductivity of 58 million Siemens per meter. Anything below 57 million gets rejected and reprocessed. They also do bend testing, thermal cycling, and microscopic inspection. The rejection rate is 6%. Copper that passes inspection ships to manufacturers making electrical wire, motors, and electronics. Kennecott produces 300,000 tons yearly, but global production is 25 million tons because demand is enormous. Without copper, no electrical grid exists as we know it. Thomas Edison tried iron wire for electrical distribution in the late 1800s. It didn't work. Resistance was so high that power couldn't travel more than a few blocks. Without copper, electrical power is limited to buildings with their own generators. No power lines between cities. Every building needs its own coal or diesel generator running constantly. The internet is physically impossible. Fiber optics carry data long distances, but electronics at each end require copper for power and short-range transmission. Data centers use thousands of miles of copper cabling. Without copper, you might have mechanical telegrams, but no electronics, computers, or digital communication. Electric motors don't exist in practical form. Every motor requires copper windings for electromagnetic fields. Aluminum motors are 3 times larger for the same power, overheat easily, and fail quickly. Without copper motors, manufacturing never industrialized beyond steam power. Modern factories don't exist. Every product is more expensive because it's made by hand. Transportation is completely different. No electric trains. You're stuck with diesel locomotives. No electric cars. Tesla doesn't exist because you'd need a 6,000-pound aluminum motor to move a 2,000-pound car. Ships use massive diesel engines instead of efficient electric systems. You've seen how copper ore concentrates from 0.6% to 30% through flotation, how 2,200-degree smelting separates copper from impurities, how electrolytic refining creates 99.99% purity, making efficient electrical transmission possible, and why the aluminum wiring crisis proved copper can't be substituted. If this interested you, subscribe for more deep dives into materials making modern life possible. Thanks for watching. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the 4th most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These 3 countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the U.S. Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, Demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed, because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. the carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings, and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones, because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3 thousandths of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high volume production. There's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of % and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste. Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, enough. Imagine a huge meeting of Chinese officials where the decision rang out, we're done accepting other people's trash. They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, that's it, take it all back. My garage is full and I'm sick of this. And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories: wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents. A modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it. A giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about a quarter pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide a resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation: drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Jizan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian Tunnels. Toronto TTC North Subway Extension, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. Every year, millions of tons of metal waste get recycled worldwide, but only at the very end of this massive process does a substance emerge that's heavier than almost anything you've ever held in your hands. Picture a metal where a tiny piece weighs as much as a brick, and extracting it is more like hunting ghosts through fire and acid. Today, we're stepping inside a facility where one of the rarest and most mysterious metals on the planet is born from dirty sludge: osmium. But the most shocking part isn't its weight. It's what you have to go through to get even one small bar. And trust me, if you stick around until the end of this video, you'll learn a fact about this metal that literally breaks logic and makes you question the laws of physics. We're now entering the primary processing facility for platinum sludges. Everything around here is humming, steam's bursting out from under valves, and the workers look like they're gearing up for a flight to another galaxy based on the sheer amount of protective gear they're wearing. And that's no surprise. Osmium is basically the heavyweight champion of the periodic table, and it doesn't tolerate amateurs. It's twice as dense as lead. Just think about that for a second. If you grab a cube of this metal with sides only 4 inches long, it'll weigh nearly 22 pounds. That's like trying to pick up a full-grown cat that's compressed itself down to the size of a matchbox. The process of extracting osmium is a real adventure for anyone who loves complex flowcharts and intellectual challenges. This metal doesn't just lie around in proud nuggets deep in the earth, waiting for some lucky prospector to pick it up and slip it into their pocket. Nope, it's way trickier than that, and hides itself in the residues left over from the industrial purification of copper and nickel. Picture a whole mountain of rock that's already been processed, squeezed for everything possible, and only at the very end, in the dirty sludge, this heavyweight remains. You and I walk past massive vats where all hell breaks loose because the metal mixture gets hit with aggressive chlorine and insanely high temperatures. It looks like a set from a movie about the future, where humanity learned to extract value from dust. The work starts with anode slime. That's the sediment left over after electrolysis. To get to the osmium, specialists have to literally dismantle the molecular structure of this waste. First, the slime gets treated with acids to wash out the more cooperative metals. When it's our hero's turn, thermal processing kicks in. Temperatures here reach thousands of degrees Fahrenheit. This isn't just heating, it's total transformation of matter under the watch of dozens of sensors. When the mixture hits the reactors with chlorine, the most critical stage begins. Osmium reacts and transforms into a volatile compound. This gas needs to be captured with pharmaceutical precision. The slightest error in pressure or temperature, and the precious metal simply flies up the stack, leaving behind nothing but a foul smell. Special absorption towers step by step pull the gas in, converting it into a solution. It's like hunting a ghost, except instead of traps, you're using complex chemical filters. Next, the solution goes through several more purification stages until finally a precipitate appears, pure osmium salt. But that's still not the end of the road. This salt gets roasted again in a stream of hydrogen to produce that same dark blue powder. Every pound of this powder, that's the result of hundreds of workers and massive machines grinding away. Looking at these vats, you realize that osmium extraction isn't just metallurgy. It's the pinnacle of engineering genius, where every move costs thousands of dollars. This is work for the patient and the bold, because this metal doesn't forgive mistakes, but it rewards those who make it through all these fiery and chemical obstacles with its otherworldly strength. To extract it, you need to convert it into osmium tetroxide. And this is where the fun really begins, because this gas smells like someone decided to mix bleach with rotten radish and set it all on fire in a closed room. The metal's name actually comes from the Greek word meaning smell, and trust me, the Greeks knew what they were talking about. We move on to the separation laboratory. Here reigns an atmosphere of sterility that contrasts with the dirty rumble of the previous workshop. Scientists in white coats manipulate glass tubes and retorts. The whole process looks like a very expensive and dangerous cooking show. They extract osmium as a fine, dark blue powder. This powder looks beautiful, but it's incredibly treacherous. If you heat it in open air, it instantly becomes a toxic gas that can ruin not just your day, but your health for years to come. So airtightness is everything here. Look at these furnaces. They operate at temperatures that are hard to fathom, over 5,000 degrees Fahrenheit. That's way hotter than the surface of some stars. Because osmium has an incredibly high melting point, you can't just melt it in a bucket and pour it into molds. They use powder metallurgy methods here. The powder gets pressed under gigantic pressure, then sintered in a vacuum. What you get is like a metal sandwich that then becomes a monolith. It's fascinating to watch them try to cut this metal. Regular saws and drills are useless here. They just dull or snap like they're made of chocolate. Osmium is so hard and brittle at the same time that you can only work with it using lasers or supersonic water jets with added abrasives. It's a real challenge for engineers. Every disc or sphere produced costs a small fortune, because making a single part burns as much energy as a small town uses over a weekend. Why even bother with such a finicky material, you might ask? Well, besides looking like a chunk of frozen blue sky, it's incredibly wear-resistant. It's used where you need something eternal, in high-voltage switch contacts or in the tips of very expensive fountain pens used to sign peace treaties. This is one of those cases where quality justifies every cent spent and every whiff of that weird smell of ozone and chemistry. I'm standing next to a finished ingot. It's small, about the size of my palm, but when I try to move it, my muscles tense up like I'm pushing a small car. This little guy weighs about 35 pounds. You can't capture this feeling through a camera. It violates every law of logic we're used to in everyday life. You expect lightness, and you get a gravitational punch to your arms. Now we're moving into the packaging zone. Even here, everything's serious. Every gram is accounted for. Every ingot has its own certificate and number. This isn't the kind of metal you accidentally forget in your work jacket pocket. Its market price swings so wildly that investors sometimes drink more sedatives than coffee. But demand for this blue shimmer keeps growing because the world's getting more technological, and osmium, it's exactly the ingredient that makes modern electronics reliable. You know what struck me most at this plant? It's the people. They talk about this metal like it's a living creature with a really bad temper, one they've learned to respect and tame just a little. There's no room for rushing here. Every move is calculated to the inch. Every second in the furnace is accounted for. This isn't just manufacturing. It's a battle of human intellect against the physical limits of matter. We're wrapping up our tour at the finished product display. Here you'll find small parts that'll soon ship all over the world. Some will end up in spacecraft, others will become part of medical devices. And every time you hear about something incredibly strong and durable, remember this blue, smelly, and impossibly heavy metal. Hope you enjoyed this walk along the edge of the periodic table. It was tough in every sense of the word. Don't forget, the world around us is way more interesting than it seems at first glance, especially if you peek behind the fence of a big factory. It was fun showing you this metallic extreme. Until next time at new facilities, where we'll definitely find something else that'll make your eyebrows shoot straight up in surprise. Did you enjoy this format? Maybe you'd like me to prepare a detailed script about manufacturing another rare metal, or talk about the logistics of moving these heavy ingots around. This metal tank, the size of a 10-story building, holds temperatures of -300 degrees. For it to carry rocket fuel or liquefied gas, there's no room for a single mistake in those walls. One microscopic air bubble in a welding seam, and the entire tank, weighing 150,000 pounds, becomes scrap. No fixing it after. No second chance. That's why every inch of that seam gets checked with X-rays, ultrasound, and helium. The gas with the smallest atoms in nature, finding microcracks where water wouldn't even seep through. And there's one moment in this process that makes the entire factory hold its breath. Today, I'm showing you inside. It all starts with choosing the metal, and this is the first stage where everything gets really expensive. Regular steel won't cut it here. It'll just die from the cold. We use special aluminum alloys, or nickel-rich stainless steel. These metal sheets are 3/4 of an inch thick, sometimes over 2 inches if the internal pressure is going to be seriously high. For example, manufacturing tanks for liquid hydrogen demands such metal purity that it's X-rayed before it even hits the welding table. Every sheet is marked and tracked, because if there's a void or impurity hiding somewhere in the structure, it'll become a rupture point under the cold. This is the foundation that holds all cryogenic equipment safety together. The welding process is a whole other story that makes a lot of engineers go gray prematurely. You can't just grab an electrode and weld 2 pieces of metal together. We use automated plasma or argon welding under a layer of special flux. The weld has to be stronger than the metal itself. Every inch of that weld goes through 3 stages of inspection. First, there's visual examination, then ultrasound, and finally, full X-ray scanning. We're looking for pores the size of dust particles. If even one air bubble is found in the weld, that entire massive tank gets sent to the scrap heap. There's zero allowance for fixing mistakes by welding over the top. That's the answer to how you ensure hermetic sealing and safety for decades ahead. Now we're getting to the coolest design feature. A cryogenic tank is actually two vessels, one inside the other. It's like a Russian nesting doll, where there's a gap 6 to 12 inches wide between the outer and inner shell. The inner tank holds the actual fuel, and the outer one protects it from the environment. But the real secret isn't the double walls, it's what's between them. There has to be absolute emptiness. We create a vacuum so deep that almost no air molecules remain. This prevents heat from transferring from the warm outer shell to the super cold inner one. Without this vacuum, liquid oxygen at minus 297 degrees Fahrenheit would boil faster than water in a kettle. To make this thermal barrier even more effective, we use what's called multi-layer insulation. Workers manually wrap the inner tank with dozens of layers of special foil and fiberglass. It looks like we're preparing a giant baked potato for giants. Each layer acts like a mirror, reflecting thermal radiation back into space. In other cases, we fill the gap between the walls with perlite, a volcanic sand we puff up into light white beads. It takes thousands of pounds to fill all the voids. Vacuum insulation testing takes weeks. Powerful pumps run day and night, sucking out air until sensors show the required level of vacuum. It's tedious, but a critical stage, because the vacuum is the only thing standing between calm gas storage and a massive explosion. The scale of these structures is mind-blowing. Some liquefied natural gas storage tanks stand over 100 feet tall and can hold millions of gallons of fuel. The weight of such an empty tank can reach 150,000 pounds. When it's filled, the load on the foundation becomes colossal. This isn't just a barrel on legs. It's a complex engineered structure with its own system of valves, sensors, and evaporators. All of this has to work in conditions where ambient temperature can swing from minus 30 to plus 110 degrees Fahrenheit, while inside, eternal winter reigns. The space industry is the main customer for these technologies. A rocket needs liquid oxygen and hydrogen to break free from gravity's grip. If a tank at the launch site springs a leak, a launch worth hundreds of millions of dollars gets scrubbed. But cryogenics aren't just for flights to Mars. Energy and industry consume these technologies in massive quantities. The whole world is now shifting to liquefied natural gas, and you can't transport or store it without these steel thermoses. Medicine, where liquid nitrogen is used to store biological materials at minus 320 degrees Fahrenheit, also depends completely on the quality of these welds. The most nerve-wracking moment at the factory? The helium leak test. Helium is a gas with incredibly tiny atoms that can slip through any microscopic crack where even water or air would get stuck. We pump helium into the inner tank at 500 pounds per square inch and scan the outer surface with special detectors. Sniffers. It's like finding a needle in a haystack, except if we find the needle, we have to explain to the customer why delivery just got pushed back a month. Nobody smiles here until the instrument shows absolutely zero leakage. This is the final exam for the entire factory crew. If you've ever wondered how cryogenic tanks work, here's the deal. They run on pressure differential. When we draw gas from the tank, a small portion of the liquid converts to vapor, maintaining constant pressure inside. It's a self-regulating system, but it demands perfectly calibrated hardware. All those valves and pipes are also made from special alloys and put through cold testing. We freeze them in liquid nitrogen baths to make sure they won't seize up at the worst possible moment. Another thing that blows your mind: how these giants get transported. When a tank 80 feet long rolls out of the factory gates, it becomes a full-on military operation. Special platforms with dozens of wheels slowly haul it to its destination. We have to be absolutely certain that during all that bumping on the road, the inner tank doesn't rip away from its supports. Those supports, by the way, aren't made of metal. They're made of special composite plastic, because metal conducts heat way too well. It's another tiny detail that shows just how complex the manufacturing really is. Right now there's a lot of talk about the hydrogen economy, and that means demand for these tanks is going to explode thousands of times over. But the number of facilities that can maintain these quality standards remains incredibly small. This isn't production you can scale up overnight. It takes years to train a welder to work with these alloys, and even longer to dial in the vacuum systems. This is a world where we're playing very dangerous games with physics, and so far, we're winning. I hope you found it fascinating to look at these steel giants and understand why they cost as much as a small fleet of luxury cars. This is where the ability to use our planet's most energy-efficient fuel is born. We walked through the workshops, witnessed plasma welds, and felt the chill of future vacuum. It's been a wild journey into a world where minus 300 degrees is just a normal working temperature. Thanks for joining me on this tour. Hit that like button if you were blown away by the idea of holding a vacuum inside a tank the size of a house. Subscribe to the channel, because we've got plenty more factories ahead where they create things most people don't even know exist. We'll show you a world made of steel, fire, and incredibly precise calculations. See you in the next review, where we'll be hunting for engineering truth once again in the roar of working machinery. Take care, and keep your pressure in check. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? You can find in ordinary dirt that contains so much energy, 2 pounds replaces 6 million pounds of coal. A rock you shouldn't touch with bare hands, controlled more strictly than gold, and determines whether entire cities have power in winter. This is uranium ore, the planet's most controversial geological resource, simultaneously saving us from climate catastrophe and threatening nuclear apocalypse. Let's dive into a world where geology collides with nuclear physics, and ordinary stone can change the fate of civilization. Let's start with what uranium ore actually looks like. If you're picturing something bright green, glowing in the dark like those mutant movies, I hate to break it to you, most uranium ore looks like regular gray or yellowish brown rock, sometimes with a greenish tint, sometimes with black spots, but nothing particularly mind-blowing. You could walk right past this stuff in the mountains and never even know it's radioactive. True, there are minerals like uraninite or torbernite that have a brighter yellow-green color, but that's more the exception. Real glow happens, but not from the uranium itself. Some uranium minerals fluoresce under ultraviolet light. They light up bright green or yellow. Geologists use this to find deposits. They shine UV lamps in the dark, and the ore gives itself away with that glow. Looks straight up cosmic, especially in caves, where the walls suddenly burst into neon colors. But the main feature of uranium ore isn't its appearance, it's what's inside. Uranium-238 and uranium-235 are isotopes that slowly decay, releasing radioactive radiation for billions of years now. 1 gram of uranium emits around 12,000 radioactive particles per second. Not enough to kill you instantly, but enough to build up a dangerous dose over years if you constantly carried a rock like that in your pocket. Uranium is found everywhere, in rocks, soil, water, even seawater. The average concentration in Earth's crust is about 3 parts per million. That means in every ton of ordinary dirt, there's roughly 3 grams of uranium. But for industrial mining, you need concentrations at least 100 times higher, from 0.3% and up. Deposits like that are rare and only form under specific geological conditions. The richest deposits are found in Kazakhstan, Canada, Australia, Niger, and Namibia. Kazakhstan leads in production, about 45% of global output. Canadian deposits in the Athabasca Basin contain ore with uranium concentrations up to 20%. That's fantastically high. For comparison, most deposits have between 0.1 and 1%. How do you mine uranium ore? There are 2 main methods: traditional shaft mining and in-situ leaching, which sounds like something from a sci-fi movie but actually works. In the first case, you dig a mine or an open pit, blast the rock with explosives, load it onto dump trucks, and haul it to a processing plant. Just like any other ore, except with radiation. Miners work under special conditions: constant radiation monitoring, dosimeters on every worker, limited time in high radiation zones. The air in the mines can contain radon, a radioactive gas released when uranium decays. It's constantly pumped out by powerful ventilation systems. Without this, miners would receive dangerous radiation doses in a matter of months. Now, about in-situ leaching. Instead of digging a mine, they drill boreholes straight down to the ore deposit at depths of 300 or 600 feet. Through some boreholes, they pump in a solution, usually sulfuric acid with an oxidizer, or soda solution, depending on the type of ore. This solution dissolves the uranium right there underground. Through other boreholes, they pump out the solution that now contains dissolved uranium. At the surface, they extract the uranium from this solution using chemical methods. Underground leaching is cheaper, safer for miners, and less destructive to the environment. You don't have to haul millions of tons of rock to the surface. That's how most uranium is extracted in Kazakhstan. But the method only works for certain types of deposits where the ore sits in porous sandstone that a solution can filter through. After extraction, the ore needs processing. It's crushed, ground up, and also treated with acid or alkali to dissolve the uranium. What you get is a solution containing uranium, along with a bunch of other elements: iron, calcium, sulfur, rare earth elements. This solution is purified, and the uranium is precipitated as a concentrate called yellow cake. Though it's not always actually yellow, it can be greenish, brown, or black depending on the impurities. Yellow cake. That's uranium oxide with a concentration of about 80% uranium. Looks like a powder or a sintered mass. This is already a concentrated product that gets shipped to the next stage of processing. But it's still natural uranium, a mix of isotopes, where uranium-238 makes up 99.2% and uranium-235 only 0.7%. And for nuclear fuel in most reactors, you need to enrich uranium-235 up to 3 to 5%. Uranium enrichment. That's a separate high-tech industry, wrapped in secrecy and international controls. First, yellow cake gets converted into gas. It's the only uranium compound that easily transitions to a gaseous state under normal conditions. Though normal conditions here means a temperature around 140 degrees Fahrenheit with a slight increase in pressure. Then, this gas is run through thousands of cascades of centrifuges or gas diffusion plants. The centrifuges spin at around 100,000 revolutions per minute, so fast that the outer edge moves at nearly the speed of sound. At this rotation speed, heavier molecules containing uranium-238 concentrate slightly more near the walls, while lighter ones with uranium-235 stay closer to the center. The difference is tiny, which is why thousands of sequential stages are needed. The entire enrichment process takes months and consumes enormous amounts of electricity. A single enrichment facility can use as much power as a medium-sized city. That's why these plants are built next to major power stations or in countries with cheap electricity. And this is where geopolitics comes in. Those same centrifuges can be used to enrich uranium, not to 5% for power plants, but to 90% and beyond for nuclear weapons. That's why the international community tightly controls who gets access to these technologies. The Atomic Energy Agency conducts inspections, verifies that countries are following agreements and not building weapons under the guise of peaceful energy. Enriched uranium gets converted back into solid form, uranium dioxide. From it, they press small cylindrical pellets roughly ½ an inch in diameter and about 2/3 of an inch long. These tiny pellets contain as much energy as ½ a ton of coal, or around 130 gallons of oil. Hundreds of these pellets get loaded into long metal tubes made of zirconium alloy, fuel rods, and hundreds of rods form a fuel assembly for the reactor. A single modern nuclear reactor, 1 gigawatt of power, holds about 100 tons of uranium fuel. That's enough for 3 to 4 years of operation. During that time, the reactor generates enough electricity to power a city of 1 million people for those entire years, all from 100 tons of uranium. By comparison, a coal plant with the same output burns through roughly 10 million tons of coal over that same period. But there's a dark side. Spent nuclear fuel is the most dangerous waste humanity has ever created. After 3 to 4 years inside a reactor, the fuel becomes saturated with fission products, radioactive isotopes like cesium-137, strontium-90, iodine-131, and many others. Some of them stay radioactive for thousands of years. A single fuel assembly radiates so much that it can kill a person in minutes from just a few feet away. Spent fuel is first stored in water pools right at the plant. The water cools it and shields the radiation. After a few years, once the most active isotopes have decayed a bit, the fuel can be moved to dry storage, thick-walled containers made of concrete and steel. These containers need to last hundreds of thousands of years, until radioactivity drops to safe levels. Where and how to store them that long? A question humanity still doesn't have a good answer to. Some countries reprocess spent fuel, extracting unburned uranium and newly created plutonium, which can be used again. France, the UK, Japan have such facilities. But reprocessing is expensive, complex, and creates additional risks of nuclear materials spreading. The US decided not to reprocess and to simply store spent fuel, waiting for a solution to the problem in the future. Control over the uranium fuel cycle, from mining to disposal, is a matter of national security. Countries with a complete cycle gain energy independence, but also the potential ability to build weapons. That's why the spread of these technologies is tightly controlled by international treaties. The Nuclear Non-Proliferation Treaty recognizes 5 nuclear weapon states and prohibits others from developing nuclear weapons, though it allows peaceful use of atomic energy. But reality is more complicated. India, Pakistan, North Korea built nuclear weapons without signing the treaty or by violating it. Iran is developing a uranium enrichment program, claiming it's for energy, but raising Western suspicions. Israel has nuclear weapons, though it doesn't officially acknowledge it. Uranium ore and the technologies to process it have become tools of global politics. Uranium mining also has environmental consequences. Tailings ponds, massive waste piles left after uranium extraction, contain radioactive elements, heavy metals, and chemical residues. If improperly contained, they contaminate groundwater for decades. There are stories of towns abandoned due to radiation pollution from uranium mining. For example, the city of Meilusu in Kyrgyzstan is surrounded by millions of tons of radioactive waste from the Soviet era, which still poses a danger today. But there's another side to this. Nuclear power provides roughly 10% of the world's electricity with virtually zero carbon emissions. In France, nuclear plants generate 70% of the country's electricity, giving it one of the lowest per capita carbon footprints among developed nations. In the context of the climate crisis, nuclear energy is viewed as a necessary component of the transition to a low-carbon economy. How much uranium is left on Earth? Identified reserves stand at around 6 million tons, enough for 1 to 200 years at current consumption rates. But that's only what's already been found and is economically viable to extract. Potentially available resources are far greater, including uranium in seawater. There's roughly 4 billion tons of it there, though extraction is still very expensive. Your smartphone weighs 5 pounds and holds a charge for 30 minutes. Your laptop's chained to the wall because the battery dies in 20 minutes. Electric cars don't exist. The battery would weigh more than the entire car and only go 50 miles. Cordless power tools, wireless headphones, anything portable, just impossible. All because we never figured out how to mine and refine one soft silvery metal that stores more energy per pound than any other practical battery chemistry. Without this metal, we'd still be stuck with 70s technology. Nickel-cadmium batteries that weigh 10 times more, last 10 times less, and leak toxic heavy metals. Your phone would need a brick-sized battery. Today, we're going inside a facility in Nevada, where this metal is extracted from ancient underground brine. And I'll show you what properties make it irreplaceable and what the world looks like if we have to use something else. The Albemarle lithium facility at Silver Peak, Nevada, sits in a desert valley 190 miles northwest of Las Vegas and has been producing lithium continuously since 1966. 10,000 feet beneath the surface lies a massive geothermal brine reservoir containing dissolved lithium chloride that's been concentrating for millions of years. The facility pumps this brine and processes 6,000 tons of lithium carbonate annually. If lithium had never been discovered, all batteries would use nickel-cadmium or lead-acid chemistry. A lithium-ion battery stores 160 watt-hours per kilogram. Nickel-cadmium stores 40. Lead-acid just 30. To match a modern iPhone battery, you'd need 2.5 pounds of nickel-cadmium instead of 2 ounces. The phone becomes a brick. Mobile computing doesn't exist. The first stage pumps geothermal brine from wells drilled 10,000 feet deep. This brine comes up at 200 degrees Fahrenheit, carrying 300 parts per million of dissolved lithium, along with sodium, potassium, and magnesium. The brine flows into massive evaporation ponds, covering thousands of acres, where the Nevada sun and desert wind do the work. Over 12 to 18 months, the water evaporates, and lithium concentration increases from 300 to 6,000 parts per million. This creates lithium's first critical property. Extreme reactivity makes it the lightest metal that can store electrical charge. Lithium atoms give up electrons more easily than any other practical metal, exactly what you need in a battery anode. Without this, you'd need heavier metals like nickel or cadmium, which means heavier batteries for the same energy. After evaporation, the concentrated brine moves to a chemical plant where it's treated with sodium carbonate to precipitate lithium carbonate as a white powder. This powder is washed, filtered, and dried to 99.5% purity. Lithium carbonate looks like fine white sand, ready to ship to battery manufacturers. Lithium's voltage characteristics become critical here. A lithium-ion cell operates at 3.7 volts. Nickel-cadmium runs at 1.2 volts. To match lithium's voltage, you'd need 3 times as many nickel-cadmium cells wired in series, tripling the weight and complexity. A 6-cell lithium laptop battery would require 18 nickel-cadmium cells. A 1-pound battery pack would weigh 7 pounds, making laptops impossible to carry. Lithium carbonate gets shipped to battery manufacturers, where it's processed into lithium metal or lithium compounds for battery cathodes and anodes. Modern lithium-ion batteries use lithium cobalt oxide or lithium iron phosphate for the cathode and graphite with embedded lithium for the anode. During charging, lithium ions move from the cathode to the anode through the electrolyte. During discharge, they move back, generating current. This reversible movement creates unmatched energy density. A lithium-ion battery handles 1,000 cycles while retaining 80% capacity. Nickel-cadmium manages 500 cycles. Lead-acid gets 300. Without lithium, devices need battery replacement twice as often, generating toxic waste because nickel-cadmium contains poisonous cadmium and lead-acid contains brain-damaging lead. Battery manufacturers shape lithium electrodes into thin sheets and stack them with separators, creating battery cells. Multiple cells connect to form packs for phones, laptops, cars, and tools. Each application demands specific energy density and safety features, but all depend on lithium's unique properties. Lithium's power-to-weight ratio is revolutionary. The Tesla Model 3 has a battery pack weighing 1,000 pounds that stores 75 kilowatt-hours, delivering 300 miles of range. With nickel-cadmium, you'd need 6,000 pounds of batteries to match that energy, but the car weighs only 3,500 pounds total. The battery weighs more than the car. You can't build a practical electric vehicle. Tesla doesn't exist. Electric cars remain a failed experiment from the early 1900s. Every batch of lithium and every battery goes through rigorous safety testing, and there's a specific reason why lithium battery safety standards are so incredibly strict. In 2016, Samsung released the Galaxy Note 7 smartphone with a lithium-ion battery that had a design flaw. The internal structure allowed the positive and negative electrodes to touch under certain conditions, creating a short circuit. Samsung had to recall 2.5 million phones globally. The recall cost them $5.3 billion. Airlines banned the Note 7 on flights. The incident nearly destroyed Samsung's phone business and proved that lithium batteries demand perfect manufacturing with zero tolerance for defects. Today, every lithium battery undergoes crush testing, puncture testing, thermal cycling between -40 and 150 degrees Fahrenheit, overcharging, and internal short-circuit simulation. The rejection rate for lithium battery cells is around 8%. Lithium that's passed all testing gets shipped to electronics manufacturers around the world. The Silver Peak facility produces 6,000 tons annually, but global production is roughly 400,000 tons, because demand is massive. Without lithium, portable electronics barely exist. Your phone stays plugged into the wall, like it's the 80s. Laptops are 20-pound luggables with 30-minute battery life. Wireless earbuds, cordless drills, e-bikes, drones, portable medical devices, none of it exists. Anything portable and electronic requires a gas generator or an extension cord. Electric vehicles are impossible. Every automaker tried EVs with lead-acid or nickel metal hydride batteries in the 90s and 2000s. All failed. Maximum range 60 to 80 miles. Batteries died after 2 years. Without lithium-ion, Tesla never gets started. EVs remain a failed technology, and we're stuck with gas cars with no viable alternative. Renewable energy storage doesn't work at practical scale. Solar and wind need massive batteries to store energy when the sun doesn't shine or the wind doesn't blow. Without lithium, these systems would be warehouses full of lead-acid batteries weighing 50 times more, costing 10 times more, needing replacement every 3 years. Grid-scale energy storage is economically impossible. Renewable energy remains tiny because it's too unreliable without storage. Without this lightweight, high-voltage metal, we're stuck in a world where electronics stay plugged into outlets, portable devices don't exist, electric cars are impossible, and renewable energy can't replace fossil fuels. You've seen how brine containing 300 parts per million lithium concentrates through evaporation to 6,000 parts per million. How chemical processing creates 99.5% pure lithium carbonate. How lithium's properties create batteries with 4 times the energy density of alternatives. And why the Galaxy Note 7 proved that lithium production demands absolute precision. If this hooked you, subscribe for more content making modern life possible. Thanks for watching. Every year, the world builds massive icebreakers and liners that weigh as much as entire neighborhoods. But did you know their heart no longer beats inside the hull? Engineers took an insane step. They ripped out a 30,000 horsepower engine, capable of powering a city of 25,000 people, and dropped it straight to the ocean floor in a steel capsule weighing as much as 2 Boeing 747s. This is an incredibly complex mechanism where a rotor misalignment of a fraction of a millimeter can tear metal to shreds. Watch this video to the end, and you'll discover the shipbuilder's biggest secret. What fatal assembly mistake they hide underwater forever, and how an invisible enemy can destroy this beast in just a couple of days. From the outside, it looks like a massive metal tail bolted to the bottom of a ship. But inside, a full-fledged electric motor. They don't install it in the ship's hull, like they've done for decades. Here it's the opposite. The motor is immediately submerged in water, hermetically sealed in a steel casing, and made to work right there in the ocean. That's why this design is treated almost like an underwater vehicle. The idea to move the engine outside the ship's hull appeared relatively recently, although engineers themselves had been thinking about it for decades. Back in the mid-20th century, shipbuilders tried to get rid of long shafts, gearboxes, and complex mechanical transmissions that took up enormous space inside the vessel and lost part of the power. The real breakthrough came in the late 1980s, when Finnish engineers working on icebreakers for northern seas proposed a radical solution: relocate the electric motor directly into a rotating pod beneath the hull. The concept was developed by specialists at a shipbuilding company searching for a way to make vessels more maneuverable in ice. The first experiments looked risky. The motor needed to be completely isolated from seawater and made to run for years without maintenance. In 1890, the first working units appeared, and within just a few years, the technology started being installed on actual icebreakers. When it became clear that the rotating thruster allowed ships to move in practically any direction, cruise liner builders quickly adopted the system. Since then, this design has gradually changed the idea of where exactly a ship's heart should be located. Not inside it, but directly beneath it. From the outside, it looks like a massive metal tail bolted to the ship's hull. But inside is a full-fledged electric motor. It's not placed in the ship's body, the way it had been done for decades. Here it's the opposite. The motor is immediately lowered into the water, sealed hermetically in a steel casing, and made to operate right there in the ocean. That's why this structure is treated almost like a submarine vessel. I walk past sections of the hull that, just a few hours ago, were separate steel plates, each one several inches thick and weighing thousands of pounds. These are curved metal sheets several inches thick, already pre-rolled, so the future capsule will have a smooth, streamlined shape. Cranes slowly lift these elements and bring them together, like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld goes. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, going over every foot of the joint several times. First, the inner seam is formed, then the outer one, after which the surface is ground down so no protrusions remain that would create water resistance. When the hull closes up, it already looks like a smooth steel torpedo. After that, inspection begins. The seams are examined with ultrasound and X-rays, searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and welded fresh. Then the capsule is sealed and pressurized to levels way beyond what it'll face underwater. If there's a weak spot anywhere, it'll show up right away. Only after that is the hull cleared to handle years of work in cold seawater and constant ice impacts. Once the steel capsule is fully welded and pressure tested, they need to install the electric motor, the main power source for the future vessel. And that's when you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform and looks more like part of a power plant than ship machinery. Its diameter is nearly 10 feet, and it weighs so much that regular lifting equipment isn't even considered. Only heavy overhead cranes do the job. The rotor, the rotating part of the engine, gets lifted separately. This massive metal ring with copper conductors weighs more than a fully loaded truck. The crane starts moving so slowly, it's almost invisible to the eye. The operator works off signals from several engineers standing on different sides of the housing, constantly monitoring the component's position. There's no room for sudden movements here. Even a fraction of an inch displacement could mean misalignment that'll show up during operation as severe vibrations. They literally lower it inch by inch, constantly measuring clearances with laser instruments. Bearings and support elements are already installed inside the housing, and all of them have to align within thousandths of an inch. If the engine shaft doesn't line up perfectly with the geometric center of the capsule, rotation will create an imbalance. After the rotor's been set, engineers won't let that crane move for a long time. A whole series of checks begins. They measure alignment, hand rotate the shaft several times, listen for the sound of metal contact. Sometimes they lift the engine again and adjust its position, spending hours on just a few millimeters of shift. Everyone here understands that once the casing closes, there's no getting back inside, so perfect precision matters more than speed. When the engine finally settles into place, the whole assembly suddenly looks complete. An empty steel shell transforms into a real powerhouse. This is the moment you could call the birth of a system that will soon spin a propeller, turn a multi-thousand-ton vessel, and run for years underwater, where no human will ever see it again. And so more people can see my channel, please subscribe and comment on the video. Modern installations can pump out up to 22 megawatts of energy. That's equivalent to over 30,000 horsepower. For perspective, one of these engines could power a small town of 25,000 people. A fully assembled installation, engine and propeller combined, can weigh over 320 tons, or more than 700,000 pounds. That's the weight of 2 Boeing 747s. The propeller attached to this pod often measures over 22 feet in diameter. Each blade on that propeller weighs as much as a full-grown elephant. Once the engine is securely tucked inside its steel casing, the moment of truth arrives, mounting the propeller. If the pod itself is the muscle, the propeller is the hand pushing against the water. And here we circle back to those head-spinning scales. Each blade is forged from a special alloy of bronze, aluminum, and nickel. This metal has to be strong enough not to bend under thousands of tons of water pressure, yet smooth enough not to create unnecessary turbulence. The blades arrive at the capsule on special pallets, each one wrapped in protective film like a piece of jewelry. Installation is done using hydraulic pushers. The propeller is mounted onto the motor shaft protruding from the capsule, and here precision is once again measured in thousandths of an inch. Any misalignment will cause the propeller to vibrate at high speed, and that vibration will simply destroy the engine bearings in a matter of days. When the propeller finally seats into place, it's secured with a massive nut tightened with a force that's hard to even imagine. After that, a streamlined cap is installed on the propeller hub. This ensures the water flow past the propeller stays perfectly smooth. The entire assembly is then coated with a special paint that prevents marine organisms and barnacles from attaching. Because even a few inches of buildup on the blades can reduce engine efficiency by 5 to 7%, which translates to losses of hundreds of thousands of dollars per year. Today, I dragged you out to a place where dust isn't a sign of bad housekeeping. It's the smell of serious money and the foundation of everything we call civilization. We're at a cement plant. Look at this landscape. It's like we just landed on Mars, except instead of red sand, everything here is coated in a fine layer of gray powder. Just think about it. We produce over 4 billion tons of this stuff every year. If you tried to stack it all up, you'd get a mountain that would dwarf any skyscraper in New York. We start our journey at the very beginning, the quarry. Just look at these machines. These giant dump trucks look like they escaped from a Transformers movie, but instead of saving the world, they just haul limestone all day long. One wheel on this thing stands about 12 feet tall. That's twice the height of your average pedestrian, who's probably sipping a latte somewhere downtown right now, completely unaware that their apartment is held up by the efforts of these steel monsters. Limestone is the foundation of everything. It's ancient shells and skeletons of sea creatures that decided to die right here millions of years ago, so we could build another shopping mall today. When limestone gets blasted in the quarry, chunks of rock can be the size of a compact car. But for the plant, that's way too coarse. That's where the primary crusher comes in. It's this massive steel jaw that chews through rock as easily as you crunch chips in front of the TV. The noise here is so intense that your noise-canceling headphones would just give up and retire. After the crusher, we get chunks no bigger than 3 or 4 inches. Next, all this mass goes onto a conveyor belt that stretches for miles. It looks like an endless snake crawling through fields and roads straight to the heart of the plant. Now we enter the raw materials prep shop. This is where the cooks of the industrial world mix their secret recipe. Besides limestone, we need clay, sand, and a bit of iron ore. All of this has to be ground into a fine powder called the raw mix. You can't even imagine how precise this ratio has to be. The lab checks the composition every 15 minutes. If they're off by even 1%, your entire skyscraper might just decide it'd rather lie down than stand up. Chemistry rules everything here. It's pure science, where we make molecules dance to our tune. And now brace yourselves, because we're approaching the hottest spot on the map. This is the rotary kiln. If you ever thought summer in Texas was hot, you knew absolutely nothing about life. This kiln is a gigantic steel tube over 600 feet long. It's tilted at a slight angle and constantly rotating. Inside, it's straight up hell. Temperatures in there climb to 2,700 degrees Fahrenheit. That's so hot that iron starts to weep. At this moment, what we call decarbonization happens. The limestone breaks down, releasing carbon dioxide, and transforms into calcium oxide. This is the moment of truth. The raw material begins to melt and clump into little gray balls called clinker. Clinker is basically a semi-finished product, cement in its embryonic state. Just think about the energy needed to keep a fire like that going. They burn everything here, from coal to old car tires. So, here's something wild. Old tires make excellent fuel because they burn completely at these temperatures. leaving behind nothing but energy for our kiln. It's like nature's own brutal recycling program. When this red-hot clinker exits the kiln, it looks like tiny meteorites that just fell from the sky. It needs to be cooled immediately. Massive fans blast it, dropping the temperature from thousands of degrees down to 160 degrees Fahrenheit in just minutes. The whole thing looks incredibly dramatic. Clouds of steam, glowing metal, and that distinctive crackling sound. But this still isn't cement. The final stage is the last grinding. We take our clinker, add a bit of gypsum to it, about 5% of the total weight, and send it into a ball mill. This is another horizontal tube, but inside it's packed with thousands of steel balls. As the tube rotates, these balls drop and pulverize the clinker into such a fine dust that it becomes softer than the flour your grandma uses to bake pies. The gypsum here is needed, so the cement doesn't set instantly when you add water to it. Without gypsum, construction workers simply wouldn't have time to carry a bucket of mix to the wall. This grinding process is incredibly loud and consumes enough electricity to power a small town. But the result is worth it. Now we have a gray powder that can turn into stone on command. We store it in massive silos, these concrete towers that can reach up to 150 feet tall. Each silo holds thousands of tons of finished product. Look at these trucks lined up in queue. They haul this powder all across the country. Rail cars, barges, bags at hardware stores. Cement is everywhere. Every American indirectly consumes close to 1,000 pounds of cement each year. We literally live inside this material. Our roads, bridges, building foundations, even power plant dams. All of it depends on those gray granules we just saw inside that blazing kiln. People often tell me this is a dirty business. And yeah, it's true. There's no cement without dust and fire. But that's where its raw beauty lies. This is an industry that doesn't tolerate weakness. Everything here is massive, everything scorching hot, and everything operates at the physical limits of what materials can handle. It's a real battle between man and matter, where we force solid rock to go liquid, then solid again. But this time in exactly the shape we need. Next time you're walking down a sidewalk or staring up at bridge supports, remember the long journey that stone took. From an explosion in a quarry to 2,700 degrees inside a kiln to steel balls in a grinding mill. It's a long road, packed with chemical transformations and incredible engineering genius. We've learned to control processes that took nature millions of years to create, and we're doing it at a scale of billions of tons. I hope you enjoyed this journey through the world of dust and fire. Personally, I always love seeing how something that looks so simple on the surface turns out to be incredibly complex inside. It reminds us that behind every ordinary thing, there's an entire army of people, machines, and scientific calculations. All right, I'm off to clean the dust off my camera, and you, don't forget to look at the world around you a little more carefully. See you at the next factory, where we'll definitely find something huge, loud, and absolutely fascinating. It's interesting that even in our age of digital technology and artificial intelligence, we're still dependent on a red-hot tube filled with limestone. You can write code for a new app, but you can't live in it. You'll still need a foundation, walls, and a roof. And that's exactly why cement plants aren't going anywhere. They're a reality you can't ignore. It's physics you can't hack. And that's what I love most about it. Here, everything is real. Touch this furnace, you'll get burned. Stand under that clinker stream, you'll get buried. No filters, no fakeness, just pure industrial power. We've traveled a lot of miles today, seen tons of raw materials and giant machinery, and every single time, I can't stop marveling at the scale. Humanity, this weird creature that decided caves weren't enough and started turning mountains into powder to build its own mountains out of glass and concrete. It's ambitious, it's bold, and it's very human. And you know what else is human? Subscribing to my channel right now. Alright, that's it. Tour's over for today. The air here's getting too thick, and my lungs are already begging for some clean forest air. But I'm sure tomorrow I'll want to come back to where the big machines work, because that's where you feel the real rhythm of our world. See you. 70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains. And plastic, if we're being brief, is just very long chemical chains, break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil. The exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice? Wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building, and inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me: sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in. Oil yield drops to 0, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine, only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled, with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro-world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft or every mile of surveyed deposit is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board, it's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch, a metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's one railroad car, one single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6, if you count one in China that nobody talks about openly. Fewer factories than NFL teams. And here's the thing, this same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons 600 times more than zirconium. 600. That makes hafnium the emergent.
Pick a single strand of your hair and look at it. Now imagine a thread 5 times thinner than that. So fine you can barely see it on your fingertip. That thread is stronger than steel. Not a little stronger. By weight, more than 10 times stronger. Bundle a few thousand of them together, weave them into a sheet, and you get the skin that wraps the wings of an F-22 and an F-35. The fastest, deadliest fighter jets ever built fly on a material that starts as something soft and white, like plastic yarn. And here's the part nobody tells you. To turn that soft white thread into something that can hold a 40,000-pound jet together at twice the speed of sound, you have to nearly burn it alive. Stay to the end, because the moment the color changes from white to black is the moment a fiber becomes one of the most valuable engineered materials on Earth, and almost nobody has ever watched it happen. Let's start with what this stuff actually is, because the numbers don't feel real until you hold them up against something you know. A single carbon fiber filament is about 5 to 10 microns across. A micron is 1,000th of a millimeter. Your hair runs around 70. So we're talking a thread you literally cannot split with your eye. Now take that thread and pull on it. Aerospace-grade carbon fiber holds a tensile strength of roughly 3 gigapascals. In plain terms, by weight it beats mild steel more than 10 times over. Steel sinks, this floats and shrugs off the load. That combination, almost no weight plus brutal strength, is the holy grail for anyone building something that has to fly. Every pound you cut off an aircraft is a pound of fuel you save, or a pound of missile you can carry. And it all begins with a spool of soft white fiber called PAN, polyacrylonitrile. About 90% of all the carbon fiber on the planet is born from that one white thread. It looks like nothing. It looks like fishing line, but it's the seed of the whole thing. So how do you turn fishing line into something that builds a fighter jet? You torture it with heat, in stages, and the first stage is the one that changes everything. The white PAN fiber gets pulled, slow and steady, through a series of ovens filled with ordinary air, heated to between 200 and 300 degrees Celsius. That doesn't sound like much next to what's coming, but watch what it does. As the fiber crawls through that heat, held under tension so it can't shrink and curl, its molecules lock together into tight, ladder-like rings. And the color shifts, white to yellow to a deep brown to black. You can see it happen down the length of the oven, like a slow fuse burning in slow motion. This step is called oxidation or stabilization, and it is the make or break moment. Get the temperature wrong by a little, rush the speed, and the whole batch is ruined. Here's the catch that makes this material so rare. Every factory guards its exact recipe. The precise temperatures, the precise tension, the precise speed through the oven are some of the most closely held secrets in the industry. 2 companies can buy the same white pan, and one comes out with aerospace gold, and the other comes out with garbage. That single difference is worth billions. Now comes the fire that actually creates the carbon. The black, stabilized fiber leaves the air ovens and enters a sealed furnace with no oxygen at all, just inert gas, because at these temperatures, even a whiff of air would make the fiber simply burn away to ash. Inside, the heat climbs past 1,000 degrees Celsius, and for the highest grades, it pushes toward 2 and even 3,000. Think about that, 3,000 degrees, hotter than molten lava, hotter than most metals can survive. And the fiber doesn't melt, it transforms. Everything in that thread that isn't carbon, the hydrogen, the nitrogen, the oxygen, gets blasted out as gas and driven off. About half the original mass vanishes into thin air. What's left behind is over 90% pure carbon, with the atoms locked into long, tight sheets running the length of the fiber. That alignment is the secret to the strength. The atoms are gripping each other in nearly perfect rows, end to end, so when you pull, you're pulling against the raw bonds of carbon itself. This is no longer plastic, it's no longer yarn. It is a thread of nearly pure crystal carbon, thinner than a hair, that you could hang a small car from. But a single thread, no matter how strong, is useless on its own. You can snap one filament with your fingers. The magic is in the numbers. Those filaments get bundled into what's called a tow, and a single tow can hold 3,000, 12,000, even 24,000 individual fibers running side by side. From there, they get woven, on looms that look almost like an old textile mill, into flat black cloth. Run your hand over it and it feels like dark silk, but it shimmers and it's bone dry and it weighs almost nothing. That cloth still isn't a wing though. To build the skin of a jet, the fabric gets soaked in epoxy resin, layer on layer, the threads turned in different directions so it's strong in every direction at once. Then the whole stack goes into a mold, gets sealed in a vacuum bag, and rolls into an autoclave, a giant pressurized oven the size of a tunnel. Under heat and crushing pressure, the resin flows, the air bubbles get squeezed out, and the layers fuse into one solid piece. Because a single hidden air pocket, one bubble you can't see, becomes a weak spot that could split open under the stress of flight. When it comes out, it's lighter than aluminum, stiffer than steel, and shaped like the exact curve of a fighter's wing. So where does all of this end up, and why should you care? Look at almost anything that flies fast or far today. The F-22 Raptor, the F-35, their wings and skins are packed with this material, around a third of the entire jet by weight. The Boeing 787 that carries people across oceans is half carbon fiber composite, wings and body. And here's the twist on the price. The raw fiber, by the gram, is actually cheap, just a few cents. But by the time you've turned white PAN into pure carbon, woven it, layered it, and cured a flawless, certified, defect-free part stiff enough to survive a dogfight, you're looking at a finished material worth thousands of dollars for every kilogram in the air. And the program that flies on it, the F-35, runs well over $1 trillion across its life. That's the real story of carbon fiber. A thread thinner than your hair, born soft and white, nearly burned to death in 3,000 degrees, reborn as black crystal, and woven into the wings that rule the sky. Next time you see a fighter jet carve across the clouds, remember what's holding it together up there. And if you want to see how the engines that push those jets past the speed of sound are forged, that one's even harder to believe. Keep watching.
This thing takes up 2,000 square feet and weighs 800 tons. It's called a megapress, or gigapress, and over the last 3 years, it's changed how electric trucks are made just as radically as Ford's assembly line changed the auto industry 100 years ago. There are fewer than 30 of these machines in the world. A few of them are right here. And here's the kicker. Without them, a modern electric truck simply can't cost little enough for anyone to buy it. Intrigued? Then hit that thumbs up and let's go. Ready? I'll start with the problem, because without it, I don't understand why you'd even build such a monster. The body of a regular truck, or SUV, that's 200 to 400 separate stamped steel parts, welded together on a complex assembly line. Each part, its own die, its own station, its own welding robot, its own quality control. It's slow, expensive, and hard. And for an electric vehicle, it's critical for another reason. The battery weighs anywhere from 1,000 to 1,800 pounds, and if the chassis underneath is assembled from hundreds of metal pieces joined with weld seams, in a serious impact, the whole thing can come apart in ways the crash test never predicted. That's exactly why engineers came up with the idea of casting the entire rear or front section of the body, complete with all the brackets, reinforcements, and mounting points, in one single piece. One casting instead of 40 separate chunks. That's what the megapress does. The material, an aluminum alloy. Not the kind that goes into beer cans, but a specially engineered composition based on aluminum with additions of silicon, magnesium, and several other elements in precise proportions. The main requirement for it has to stay plastic during impact and not shatter into pieces. Sounds obvious, right? But with aluminum, this is actually incredibly difficult to achieve at these wall thicknesses. From about 1/10 of an inch to just over 1/6 of an inch in different zones of the casting. Developing this alloy for a specific press and specific part geometry took some manufacturers anywhere from 2 to 4 years. One factory spent over $150 million on materials, science research, and testing alone, before the first production parts even came off the press. This press develops forces from 6,000 to 9,000 tons. 6,000 tons. That's roughly the weight of 12,000 mid-size cars compressed into a single point. The two halves of the die slam together, and in that instant, there can't be even a microscopic gap in critical zones. Otherwise, molten aluminum bursts through as what's called flash, and the part gets scrapped. A die for a large structural casting weighs between 100 and 140 tons and costs $50 to $80 million. One die. And it's already baked into the price before the first car rolls off the line. They load aluminum into a melting furnace right next to the press and heat it to 1400 degrees Fahrenheit, the temperature where metal becomes liquid and flows like water. But you can't just pour it into the mold. At that temperature, it oxidizes in seconds, and pores and inclusions appear in the part's body, drastically reducing strength. So the metal flows through a system of vacuum channels. At the moment of the shot, air is evacuated from the mold surface to a pressure below 4 millibars. That's about 250 times less than atmospheric pressure. The aluminum rushes into this vacuum at speeds from 20 to 35 feet per second and fills the entire mold cavity in 80 to 120 milliseconds. A human blinks in about 150 milliseconds. That means a part the size of half a truck is cast faster than you can blink. Right after filling, the press plunger compresses the metal with up to 9,000 tons of force. This is called intensification, which eliminates residual porosity and densifies the structure in critical zones. The whole thing, from mold close to mold open, takes between 120 and 180 seconds. 3 minutes, and you've got a complete rear body section for an electric truck that used to require 240 parts and 80 welding operations. But here's where the real risk begins. At that fill speed and that pressure, the die wears out. In the highest stress zones, where the metal flow is hottest and where the intensification pressure peaks, the tool steel starts to crack microscopically after just a few thousand cycles. It's called thermal fatigue, the same thing that happens to metal that's heated and cooled over and over. After roughly 5,000 to 8,000 cycles, the die gets pulled, sent out for repair and replacement of inserts in critical zones. That takes 3 to 5 days and costs anywhere from $300,000 to millions of dollars per repair. Servicing a single die over its full service life, 100 to 200,000 cycles, can cost more than the die itself. And all of that is baked into the cost of every single part. After pressing, the casting goes to X-ray inspection and CT scanning. The scanner penetrates the metal and builds a three-dimensional model of the internal structure. The algorithm compares it to a reference model and automatically flags zones with porosity, inclusions, or incomplete filling. If there's deviation in a critical zone, the part gets scrapped. The rejection rate when developing a new casting type runs from 10 to 20%. In mature production, 2 to 4%. Doesn't sound like much, but every rejected part means $250 to $400 of aluminum going back to the melting pot. Heat treatment after casting isn't optional, it's mandatory. The part goes into the furnace for solution annealing at temperatures between 1850 and 1900 degrees Fahrenheit for 2 to 3 minutes, then water quenching, then artificial aging at 350 degrees for 4 to 6 hours. This sequence transforms the aluminum from its as-cast state into one where it's simultaneously strong and ductile. Tensile strength roughly doubles compared to untreated castings, from 25 to 30,000 pounds per square inch, up to 45 to 50,000. That's comparable to sheet steel, but at 30 to 40% less weight. Coming out of the heat treatment oven, the part heads to machining, milling of mating surfaces and drilling holes for suspension mounts, battery packs, and body panels. Precision here is plus or minus 0.02 of an inch on datum surfaces. Then laser measurement of geometry, at 120 to 200 control points. If the part warped during heat treatment more than 3/1000ths from the reference, it goes for rework or gets scrapped. Why are only a few factories in the world doing this right now? First, the press itself. Made by 1 or 2 companies globally, the wait for a new machine, anywhere from 80 months to 2.5 years. Price tag, $50 to $80 million a unit. Second, the building. A press like this needs a facility with ceiling height no less than 40 feet and flooring that can handle loads from 800 to 1,200 tons on the support pad. Building such a facility from scratch, another year to 18 months and $30 to $50 million. Third, people. An operator for this press goes through 6 to 12 months of training, and an experienced technologist who knows how to dial in casting parameters for a new alloy and new geometry. That's someone who simply isn't available on the open job market. I watched the press open after its cycle, and a robotic arm pulled out a casting the size of a bed. The part is still steaming. It's hot, around 500 degrees Fahrenheit, and grey. And in this single part, every bracket is already built in. Every structural rib, every mounting point. 240 pieces, now one. 80 welding robots, not needed. This is why electric truck manufacturers are willing to pay $80 million for the mold and another $80 million for the press, because if they don't do it, someone else will, and then their vehicle's production cost will be $3,000 to $4,000 less than yours. In a business this competitive, that's a death sentence. Subscribe. The next project is already in the queue, and it's going to be even bigger. Drop a comment telling me where you're from. Maybe next time I'll come to you. Every year, the world mines millions of ounces of a metal most people never even think about. But without it, modern civilization would literally grind to a halt. What if I told you there's a metal hiding in every car that can absorb hydrogen hundreds of times its own volume, operate at temperatures over 5,000 degrees Fahrenheit, and cost more than gold? Palladium seems invisible, but it's what cleans the exhaust from millions of vehicles, drives key chemical reactions, and determines the price of entire industries. Where does it come from? Why is there so little of it? And what hidden detail at the end of this video will change how you think about this metal forever? Stick around to find out. Palladium is a chemical element from the platinum metals group that combines rarity, high chemical stability, and exceptional physical properties. In the periodic table, it has atomic number 46 and a silvery white color that persists even after prolonged exposure to air. At a density of around 7 pounds per cubic inch, it's lighter than platinum, yet strong enough to withstand significant mechanical stress. Palladium's melting point sits at approximately 2,830 degrees Fahrenheit, and it boils at temperatures exceeding 5,400 degrees Fahrenheit, making it suitable for high thermal load applications. One of palladium's most fascinating features is its ability to absorb hydrogen in amounts hundreds of times greater than its own volume. At room temperature, the metal literally pulls hydrogen atoms into its crystal lattice, forming solid solutions. This property is actively used in hydrogen purification technologies, membrane systems, and alternative energy research. Palladium maintains its stability and doesn't crumble, which sets it apart from many other metals. The industrial importance of palladium is enormous. The bulk of global consumption goes into catalytic converters for automotive exhaust systems. In these devices, palladium accelerates the oxidation of carbon monoxide and unburned hydrocarbons, converting them into less harmful compounds. A single passenger car might use only a few hundredths of an ounce of the metal, but with millions of vehicles in play, total demand hits tens of thousands of pounds per year. It's this industry that makes the palladium market incredibly sensitive to shifts in global auto production and environmental regulations. Beyond the automotive world, palladium is everywhere in electronics. It shows up in multi-layer ceramic capacitors, contact assemblies, connectors, and microchips. Thin palladium coatings shield components from corrosion and wear, maintaining stable conductivity even after thousands of power cycles. In electronic components, the metal's mass is usually measured in fractions of an ounce, or even grains, but collectively these amounts carry serious economic weight. Jewelry wouldn't be the same without palladium. It's added to gold alloys to create white gold without using nickel, crucial for people with sensitive skin. Pure palladium is used to make rings, earrings, and watches because it's lighter than platinum and more comfortable to wear. Palladium pieces hold their shape, don't tarnish, and rarely need polishing. Geologically speaking, palladium is pretty rare. Its average concentration in Earth's crust is just a few millionths of a percent. Major deposits are tied to magmatic complexes and sulfide ores, where palladium occurs alongside platinum group metals, nickel and copper. Mining often takes place at great depths, sometimes several thousand feet below the surface, which makes the process significantly more complex and expensive. Because of this, the price of palladium can fluctuate sharply depending on the political stability of mining regions and the state of the global economy. The chemical behavior of palladium makes it valuable in laboratory practice. It's one of the key catalysts in organic synthesis reactions, particularly in carbon-carbon bond formation processes. Thanks to this, palladium plays an important role in the production of pharmaceuticals, agrochemicals, and specialty polymers. Even microscopic amounts of the metal, measured in milligrams or grains, can substantially impact the speed and selectivity of reactions. Palladium's physical properties are equally noteworthy. It responds well to cold working, rolls easily into thin sheets, and draws into wire. From a single ounce ingot, you can produce a sheet covering several square feet. At the same time, the metal maintains high electrical and thermal conductivity, making it useful in specialized technical applications. Palladium is almost never mined by itself. It's a byproduct of nickel, copper, and platinum metal extraction. Everything starts in underground or open-pit mines, where sulfide ore is pulled from depths of hundreds or thousands of feet. The ore is crushed and ground into a fine powder, then mixed with water and reagents and subjected to flotation. The result is a concentrate enriched with copper and nickel sulfides and traces of palladium. Next, the concentrate gets roasted in furnaces at temperatures exceeding 1600 degrees Fahrenheit, stripping away sulfur and organic residues. The resulting material is melted, separating into a metallic phase and slag. At this stage, palladium is still mixed with other platinum group metals. Separation begins at refineries, where alloys are dissolved in acids and subjected to multi-stage chemical purification. Platinum, rhodium, and iridium are precipitated sequentially, while palladium is isolated as salts, which are then reduced to metal. The final stage of palladium extraction begins when, after a long chain of chemical purification, the metal has been separated from other platinum elements and exists as salts or spongy precipitate. This material is thoroughly rinsed with distilled water to remove traces of acids and impurities, then dried in furnaces at temperatures of several hundred degrees Fahrenheit. It looks like a gray-black powder with very low bulk density, which doesn't yet have the properties of compact metal. Next, the powder or palladium sponge is fed into melting facilities. Most commonly, induction or electric arc furnaces are used, where the metal is heated in crucibles made from inert materials. The atmosphere inside the furnace is monitored especially carefully. Argon is introduced, or the space is evacuated to prevent oxidation and losses. The temperature is gradually raised above 2,800 degrees Fahrenheit, until the palladium particles fuse into a uniform molten mass with a mirror-like surface. When the metal is fully molten, it's held in the furnace for a set period to even out the composition. Even traces of other metals are measured here in fractions of an ounce per ton, so samples can be pulled directly from the melt for lab analysis. If purity doesn't hit the target level, the melt goes back for additional refining. Only after confirming readings above 99.9% is the palladium cleared for forming. To produce ingots, the liquid metal is carefully poured into preheated graphite or steel molds. The weight of these ingots can range from a few ounces to tens of pounds, depending on customer needs. Cooling happens under controlled conditions to avoid internal stress and cracks. After solidification, the ingots are removed, weighed, marked, and the chemical composition is checked one more time. If palladium is destined for catalysts or the chemical industry, it might skip the ingot stage entirely and be turned straight into powder. To do this, the metal is dissolved again, then reduced under controlled conditions to produce particles of a specific size. This powder gets packed into airtight containers, where every single gram carries serious value. Global palladium production is typically measured in the hundreds of thousands of troy ounces per year. On average, worldwide output hovers around 6 to 7 million ounces annually, with more than 2/3 of that volume coming from just 2 countries. Another key figure, secondary recycling, mostly from used automotive catalytic converters, accounts for 25 to 30% of global supply. By comparison, for many other precious metals, the recycling share is significantly lower. In your average ore, the palladium content is incredibly tiny. We're talking a few hundredths of an ounce per short ton of rock, sometimes even less. That means to get just 1 pound of pure metal, you need to process thousands of tons of ore. That's exactly why production costs are so sensitive to energy expenses and logistics. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water-repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Houston, Texas, high noon. The sun here doesn't just shine, it presses down on your shoulders like a heavy, hot blanket. The air above the scorching asphalt shimmers with heat waves, and your lungs fill with a thick, distinct smell. A mix of heated rubber, dry prairie, and diesel fuel. I'm standing at the gates of the Jinan plant, the world's largest tire recycling facility, and I can feel the soles of my boots starting to soften on the blistering Texas ground. Today, I'm not just a tourist. I'm a witness to a massive technological alchemical process, where what the world considers waste that won't decompose gets transformed into energy, and the very foundation of the highways we drive on. Houston didn't just greet me with sunshine, it slammed me with a wall of sticky heat that folks down here in Texas call the devil's breath. But the second I stepped through the entrance to Jinan's facility, the sounds of the city, distant highway hum and rustling wind, instantly shifted into something far harsher. Industrial chaos. But chaos that's perfectly ordered, rhythmic, almost primal. The first thing that hits you isn't the sound, it's the vibration. You don't just hear it. It rattles your chest like a low bass line at a rock concert. That's the giant motors firing up the heart of the plant. And spread out before me are the real black Himalayas. Thousands, maybe tens of thousands of used tires stacked into neat but staggering mountains. Everything's here. Thin wheels from compacts that only ever touched smooth asphalt, all the way up to massive donuts from mining dump trucks, treads tall as a person. They all came here to die, so they could be born again. The smell here is something else. It's not just the stench of rubber. It's a complex cocktail of heated polymer, traces of road tar baked into the treads, and hot metal. The Texas sun mercilessly scorches these black surfaces, and the heat radiating off them makes you feel like you're standing next to an open oven. The air between the mountains has solidified. It's thick and oily. I watch as another truck rolls up. The hydraulics groan as the bed lifts, and hundreds of tires tumble down with a muffled rumble. Thump, 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 cascading to the foot of the black mountain. This sound of rubber hitting rubber layers over that same endless vibration from the plant's engines. It creates this uncanny sensation of being inside a living organism. The plant breathes with this rhythm. It's hungry, and these mountains are its food. The vibration intensifies when the feed conveyors kick on. You see these massive manipulators, like the claws of prehistoric monsters, tearing into the piles, snatching their prey. In this place, on the edge between old junk and raw material, you feel tiny. We're following the conveyor belt that leads straight into the heart of the main floor. Here, that vibration I mentioned earlier transforms into physical force, pounding against your eardrums. We approach it, the primary shredder. If those mountains of tires were a graveyard, then this machine is the industrial meat grinder that knows no mercy. The first thing that hits you is the contrast between speed and power. You'd expect the shredder to spin at breakneck speed, flinging chunks of rubber in every direction like a blender. But no, the shredder's shafts move slowly, almost lazily. But within that slowness lies colossal torque, force capable of crushing stone. It's a deliberately engineered method. Low rotational speed prevents the rubber from overheating, keeping it from melting and sticking to the blades, which would turn the machine into a gummy trap. When the next tire, say, a massive wheel from a Texas pickup, hits the rollers, something happens that makes you flinch. The tire tries to hold its shape. Its steel belt, that same skeleton that carried tons of weight on the road, puts up one last fight. But hardened blades made from special alloy dig into the tread like the teeth of a prehistoric predator. 1 second, and you hear that distinctive crunch as the steel wires inside the rubber snap under hundreds of tons of pressure. In that moment, bright, angry showers of sparks fly out of the shredder's jaws. It's the friction of the steel belt against the blades, creating miniature lightning bolts inside the machine's dark belly. The heat here becomes almost unbearable. If it was just hot outside in Houston, near the shredder, the air heats up to a temperature where the sweat on your forehead instantly turns sticky with rubber dust. You can smell the frictional heat, sharp, metallic, with notes of burnt sulfur. It's the smell of matter being physically destroyed. Dust is everywhere here. It's not just floating in the air, it's dancing in the beams of industrial lights, settling on every surface like black velvet. These are tiny rubber particles released during the tearing process. You can see chunks falling from beneath the rollers onto the exit conveyor. This isn't a tire anymore. These are shapeless, torn scraps of rubber, roughly the size of an adult man's palm. Mangled strands of steel wire stick out from them, those same cord fangs that magnets will pull out in the next stage. The chunks of shredded rubber that just passed through the shredder's jaws move along on the conveyor belt. They look terrible, torn, dirty, hot, with those same mangled steel wire threads, cord fangs, sticking out from every black edge. Right now, one of the most cinematic stages at the Jinan plant begins. We're approaching the magnetic separation zone. Above the conveyor, where chunks of tires race by in an endless stream, massive blocks hang suspended. Overhead electromagnetic separators. They hang low, almost touching the black flow, humming with voltage. What happens on the belt resembles an uprising of the dead. When a ragged chunk of rubber enters the magnet's zone, the steel threads inside it react instantly. You see it with your own eyes. Metal wire that a second ago was part of a solid framework suddenly comes alive. With savage force, it tears free from its rubber prison, dragging the entire chunk with it, or simply slipping out like a knife through butter. Metal literally shoots upward, defying gravity. It looks like strange, aggressive magic. Thousands of steel needles and twisted wires slam into the magnetic belt with a loud crash, spinning perpendicular to the main conveyor. This is that endless clacking, the sound of thousands of metal fragments hammering into the separator's steel armor. The heat in this zone is unique. The magnets consume a massive amount of electricity and generate heat themselves, mixing with the warmth from freshly cut rubber. You're standing in a cloud of a specific smell, a blend of ozone, which always accompanies powerful electromagnets, and warm, raw metal. It's the smell of a forge, but without fire. Look to the left of the main conveyor. Another mountain is growing there, a mountain of pure steel. The magnetic belt carries the captured metal beyond the rubber stream, and, where the magnetic field vanishes, dumps it into a separate hopper. You're looking at springs coiled into spirals, long sharp needles, tiny metal chips. Everything gleams under the factory lights with a cold, bluish glow, contrasting sharply against the matte black of the rubber. Stripped of its steel skeleton, the rubber moves forward into the darkest and most airtight section of the plant. Now that the metal's gone, the rubber chunks look surprisingly light, but that's just an illusion before the final battle. We're entering the secondary granulation zone. High-speed granulators transform the torn pieces into perfect rubber crumb. The air here is thick with black snow, fine dust swirling through beams of light. Each granule passes through a system of vibrating screens, where they're sorted by size down to a fraction of an inch. But the real climax lies ahead, inside the sealed steel pyrolysis reactors. We approach the long, insulation-wrapped cylinders. This is the zone of quiet energy. There's no open flame here, but inside, hellish heat reigns, 850 degrees Fahrenheit. The key secret? Total absence of oxygen. The rubber doesn't burn, it distills. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the Earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to